Okay, and we can relate, all these things we've been doing back to C++, right? When you're learning new things and working at the assembly level, right, you want to think about how that ties back into things that you've done before, right, at the C++ level. And so now here we have an example with the loop, but we'll eventually be looking at looping in the assembly level and how the loop instruction works. And we'll see that there's even some variations of the loop instruction. But so here in this case, with this sample C++ program, we have a constant called size with 5. We declared an array of integers, which integer corresponds to dword, or 4 bytes. An array of 5 integers with the values 10, 20, 30, 40, 50. And then we have a for loop here that is printing out all 5 of the elements in the array using pointer, right pointer notation. So in particular here, we have the star along with the expression array plus I inside the parentheses, because we know in C++, right, you have to take the starting address of the array, add the offset to it, and then dereference that. Now, you want to keep in mind, though, the differences between a high-level language like C++ versus, versus assembly, because we just got through looking at all 3 levels in terms of byte versus word versus dword, and how each of those worked at the assembly level. And in particular, we saw that we had to handle a byte array versus a word array versus a dword array differently, in the sense of we did increments of 1 for the byte array, increments of 2 for the word array, and increments of 4 for the dword array. Now at C++, because it's a high-level language, we want to be able to generalize everything, right? We don't want to have to write different things based on the type of the array that we're working with. So at C++, right, we just say things like star array plus I, but behind the scenes, because it's a high-level language, the compiler is also taking into account the type of the array. So if it's an array of integers, then what it's really doing, as we wrote down here, is star and then array plus I, but where the I, right, is really being multiplied by 4. Because of course we know that if it's an array of integers, each one is taking up 4 bytes. So you really have to add 4, as we discussed with dword, right? You really have to add 4 to get to the next term. But because it's a high-level language, we want to be able to generalize it, so that way we can still use code like this, even if it's not an integer array. If it's an array of maybe short integers, or an array of characters, or array of doubles, we want to be able to generalize it and use the same type of logic. So the idea is that behind the scenes, the compiler is always taking into account the type of the array. So that way we don't have to handle that directly in terms of the code that we write out. So behind the scenes, in this case with an array of integers, it's multiplying I by 4 and then adding that to ARR. But that's not something that you write out directly in C++. Or if it's an array of short integers, it would be multiplying, I times 2 and then adding it. Or if it's an array of characters, then it would be, I times 1 and then adding that to ARR. So this relates back to the things that we've been talking about, right, at the C++ level. But, we're seeing some of the fundamental differences here in terms of, things that are being done for you in a high-level language that aren't being done for you at the assembly level, right? Which is why we have to explicitly think about those details, like, do I add +1 or +2 or +4, to get to the second element? That was different between the 3 cases at the assembly level, but at the C++ level, whether we're using the star notation or the bracket notation, right, in either case, everything is in increments of 1 in terms of the value that we use to access the right location in the array. But the only reason why that works at the high-level language level is because of the extra work that the compiler is doing behind the scenes, right? And in general, you know, there at the high level language level, there's things that are being done for you, whereas at the assembly level, we have to kind of think more step by step, right, concretely about each little detail, right? Um, so we're just seeing how this is different compared to how we would think about things like, you know, processing each element in the array in at the C++ level versus at the assembly level. Okay, so we'll go ahead, let's look at a question here, and this will take us into the topic of strings, which we'll talk about strings and how that ties in with the topic of arrays, right, that we've been looking at here. And so here's the question. At this point, if you like, you can take a moment to think about this. But so we're given a sample variable declaration for our data segment, which says var1 byte 6 dup. And then in the parentheses, we actually have a string this time, which is the string COMSC 260. And then the question is just how many bytes is var1? And we haven't explicitly talked about strings yet, but just take everything that we've talked about so far and try to apply that to the question here. So again, you're given this declaration var1 byte 6 dup with the string COMSC 260, and the question is how many bytes in total is var1? So now would be a good time to pause the video and try to work through this, and then you can resume it and see if you got it correct. Okay, well, so the string here is COMSC 260 and the size specifier is byte. And the string itself is exactly 8 characters, right? Because we have the COMSC 260 and no spaces or anything else like that, right? So only those 8 characters are in the string itself. Now, if that's all we did, right? So if there was no dup operator, we can think that's going to be our starting point here. So what if we asked a similar question like this, but there was no dup operator and we just had the string COMSC 260? Well, one thing that you might remember, right, if you think back to, you know, 110 or 165, is that what is a string? You know, what is the string class in C++ really represent? Well, the string class in C++ is really represents an array of characters, but it's a dynamic array of characters, right? Because you can grow or shrink your string. And you've seen that come up also with, you know, some of your previous assignments where you worked with type string with your conversion and, for example, addition algorithms, right? Where you had to, you know, in some cases build a string, right? And you can do things like string concatenation. And that works because the string class is really based on dynamic character arrays that can grow or shrink in size. So somewhat similar to the vector class, but only for character array types, whereas vector can be used for any type. But a string is an array of characters, right? Or a sequence of characters. So first thing is we have to think about, well, okay, how many bytes are in each individual character? Well, 1, right? Because the size specifier here is byte. And so each character is going to be just 1 byte. So meaning we need 8 bits or a byte to store the C, a byte to store the O, a byte to store the M, and so on and so forth. So each of those characters is 1 byte. And the string COMSC 260, you know, since it has 8 characters, that one time, if we had the string one time, it would be 8 bytes. But we also have the dup operator, right? We're saying take that string COMSC 260, which is 8 bytes, and duplicate it a total of 6 times. So the total number of bytes then is going to be, you know, 6 times 8, which is 48. Because it follows that if COMSC 260 one time would be a total of 8 bytes, if we have 6 duplicates, then it's going to be a total of 40, right? A total of 48 bytes. So the correct answer then is going to be C there, or 48. So again, option C, or 48, is going to be the correct answer here. And with that, we'll go ahead and get back into the assembly environment. We can look at that example briefly in memory, and then look a little bit more generally at strings and how they work right at the assembly environment. So this is what we looked at right in the question. So again, that's just taking that string and duplicating it 6 times. And their variable name here in this case is str1. And then if we go to str1's location memory, right, with ampersand str1, then we're just going to see that, right? So the COMSC 260 back to back 6 times, as we're seeing here. And now we can think about strings in a more general sense as well, right? How to use them and how to set them up. Because strings, are going to be used a lot, especially with things like messages or text that you need to display on the console screen, or maybe that you're going to write to a file. So you can imagine things like, prompting the user for input, displaying a result, maybe displaying a menu to a user if it's a menu-driven program where the user has to choose a menu option. So all kinds of situations come up where we might use strings. And so a string does correspond to an array of characters, right? Meaning an array of bytes, because each individual character is 1 byte. Now, what we did here was we had the phrase or the string within a set of single quotes, right? In this case, right, also the dup operator was used, so COMSC 260. But keep in mind that that's just the same thing as the string COMSC 260, comma, string COMSC 260, COMSC 260 6 times, right? Just like we talked about before. So it'd be, if you did it as a comma separated list, then it'd be, of course, 6 times to do the equivalent thing, but that's the idea. Now, when you think about a string, a couple of things. First is that we can use either single quotes or double quotes. So remember, we're working at the assembly level, so we don't make those high-level distinctions like type string versus type char. In fact, there really is no typing system, but everything is a matter of size, right? Byte, word, D word, and so forth. So one way that you can set up a string is to put the entire phrase within a single set of double quotes or single quotes. That's equivalent to individually putting each character within the string within its own set of quotes and making it a comma separated list. So it means that these two things are the same. So we can do like we did before, right? The name of in this case, str2 by COMSC 260 with the whole phrase within a single set of quotes, where those quotes can be either double quotes or single quotes, right? Or we can individually put each character within its own set of quotes and make the whole thing a comma separated list of characters. Because these are both the exact same thing. Keeping in mind that that's exactly what a string is an array of individual characters, where each individual character in the string is 1 byte or 8 bits in memory. So here we have the C, comma, and then the O with the O in single quotes, and then the M in single quotes, the S in double quotes. Again, you can use the two quote types interchangeably, right? Single or double quotes. So these are both the same, right? The same end result in the end. Of course, it's in some ways more convenient to just put the entire string within a single set of quotes, right? Because that's going to be more compact, especially if it's a long message. Like we might want to just have an entire menu as one of our uh, things here in the data segment, where you might have several different options, like option one's addition, option two subtraction. And of course, it's more convenient to do that with one set of quotes instead of saying each individual character within its own quotes. But that nonetheless is what's really happening, right, in terms of memory. And so you can set up a string in general either way, um, with, again, the whole thing in one set of quotes or each character individually within its own set of quotes. And so relating that back to the dup operator, this is the same thing, except it's the string 6 times. So you could do that, right, either 6 times here, or you could even do it the lengthier way of each individual character, and then that 6 times, right? So either way. So that is, again, equivalent to what we did up here, right, with the dub operator. So again, the dub operator can also be used with strings, right? It can really be used with any type of value. And now, again, in C++, right, we kind of distinguish between, is this thing a number or is this thing a string? Is it a number or is it a string? But you want to keep in mind that in the end, everything is just ones and zeros, right? Everything is just binary. Everything is just a binary number, regardless of how we're using it or what the intention is. So you might recall from previous courses the concept of the ASCII code table. The idea being that every character on the keyboard has a ASCII value, which is a numeric value that represents that character. So we think of this in a high-level sense as what we call a string. And again, the idea might be that we're setting this up because we need to display a message like COMSC 260, for example, on the console screen, or maybe display a menu or a prompt or whatever it is we need to display, or maybe we're going to write it to a file. But we think in those terms in a high-level language, but here we want to keep in mind that everything is just ultimately binary data, one way or another. And so we think in terms of characters like the character C or the character O or the character M, but we want to remember that those are just numbers, right? So the character C is represented by a 8-bit number from the ASCII code table. The character capital O is represented with an 8-bit number. The character 0 is represented with an 8-bit number. So in that sense, right, you could also write out the whole thing using those numbers instead of the quotes in the character, right? So for example, instead of because we said that writing out the whole string like this was equivalent to a comma separated list, right? Where you have each individual character within its own quotes. Well, yet another way of doing it would be to look up all of the ASCII code values for each of these characters and then writing out those numbers as a comma separated list. So ASCII value for the character capital C, comma, ASCII value for the character capital O, comma, ASCII value for the capital M, and so on and so forth. Of course, right, that's not going to be as convenient as just writing out the string directly, but we at least want to have that awareness of what's really going on here. And so we'll go ahead and look at the ASCII code table, and we'll see what some of those ASCII value codes are, along with some other things that we can use here as well. Because so far, in the examples that we've written out here, we've been writing out the string itself, and that's it. In many cases, we, as you discussed before, right, in 165 or 110, a lot of times we also want to have that null terminator character at the end of the string. And again, that's useful because that just gives a clear indication in terms of memory of where the string ends. And in some cases, we might be looping through, for example, processing a string. And what's going to stop the loop is when you hit that null terminator. Especially if it's a type of loop that instead of going by the size of the string, maybe the only thing that we're looking at is the current character, the null terminator. If not, then keep going. If it is, then stop. So, and again, that would be something like maybe a while loop or a do while loop, where instead of knowing ahead of time the number of loop iterations, you're just going to keep going and keep going until you encounter that null terminator. So especially with a loop like that, right, you would need to have that as a way to know when the string is ended. So in general, we usually will also include that null terminator at the end of the string, right, to have that clear point of knowing where the string ends. So that takes up an extra byte of memory to store that null terminator. And then, other things that come up would be things like line returns, right? So if you're wanting to display these types of messages on the console screen, just like you would in C++, right? You want to think about the visual representation to the user, right? And you don't want to just have everything kind of running together. So in a C++ program, you use things like maybe end L or \n as a escape sequence code in your string to do a line return. And we can do those kinds of things at the assembly level as well. And that will once again come down to the ASCII code. So the idea is, all of these characters that we use, and that includes things like letters, like, A, B, C, uppercase or lowercase, or the digits 0 through 9, along with all the other symbols, right, that we have on the keyboard. The idea is that all of them have what's called an ASCII code, which just is a numeric representation of that character. And we'll look at that table here and see what some of them are. And so here's the ASCII code table. And again, we're not going to look at everything here, but in particular, you can see in the third column here, the uppercase A, and this is showing you what the ASCII values are for each of the characters. So for example, uppercase A is represented by the value 65 in decimal, or in terms of hexadecimal, it would be 41 hex, right? Because 65 decimal is equivalent to 41 in hexadecimal. So going back to, the example of the strings, you could also, if you had an A in the string, one way to represent it would be A, for example, within the, your single quotes or double quotes, or the number 65 as a decimal value, or the value 41 is a hexadecimal value, right? Those are all the same. So the character capital A, meaning the character capital A within single quotes or double quotes as a byte value, is the same as saying the number 65, right, as a byte, as a decimal value, or the number 41 as a hexadecimal byte value. And the uppercase letters are all one big group here, so they go up in sequence, right? So B is 66 decimal or 42 hex. C is 67 decimal or 43 hex. Over in the fourth column, you can see where the lowercase letters are. So lowercase a has ASCII code 97 in decimal or 61 in hex, since 97 decimal is equal to 61 hex. Lowercase b is the next one at 98 decimal or 62 hex. And then they go in sequence all the way with no gaps in between. So those are your lowercase letters and uppercase letters, right? And then the digits 0 through 9, right, are also part of this table. So for example, the character 0 has ASCII code 48 in decimal or 30 in hex. The character 1 has ASCII code 49 in decimal or 31 in hex, and so on. And then a few others here is you'll notice null at the very top here in column 1 has ASCII code 0. So when we talk about the null terminator, that is just, again, based on this table, that is just the number 0 itself, not in quotes, right? Because the number 0 in quotes would be the character 0, which has ASCII code 48 decimal or 30 in hex. But the number 0 as a byte is the null terminator. So that's how we represent and store the null terminator at the string. So in this case, in our string COMSC 260, if we wanted to make it a null terminated string, then after the string itself, we would say comma and then the number 0, not in quote marks. And we'll look at a couple others, other of these ASCII codes here. But for a line return, it's actually two different byte sequences here to do a line return, right, in the Windows x86 environment here that we're working out of. And the first is, if you see the entry there that says CR, or carriage return, you'll notice that that has ASCII code 13 decimal or D hexadecimal. And then if you look at the line that says LF or line feed new line, that has ASCII code 10 decimal or A and hexadecimal. So those two together, and we abbreviate that as sometimes as CRLF, right? Carriage return, line feed with carriage return first and then line feed second. So those two together in Windows, right, type environment do a line return, right? So other operating systems achieve that with just one code, but here in the Windows and x86 environment, we actually have two different codes together that do a line return. So the carriage return first and the line feed second. So the idea is if you want to control things like the spacing, then you can directly use those ASCII codes in your string as well. So for example, you could have your string and then comma ODH, right, which is 13 for the carriage return, and then comma OAH for the line feed. The two together would be one line. And then if you wanted to have, more than one extra line, then you could repeat that pairing or that sequence of ODH and OAH, depending upon how many, line returns you wanted to have. So you'd have, again, the two as a pair for each individual line return that you want to have. So if you wanted to have, two extra lines, you could do ODH, comma OAH, comma ODH, comma OAH. And then at the very end, right, you would have that null terminator, which is just number 0. So that just gives you an idea of how we can, fully take advantage of everything that's established here with this ASCII code table. And so the main part here is you're seeing 128 entries, right, for all these different values. And then we also, because it is a byte, right, we also can really have in total 256 values. So down here, you're seeing the extended values, which are just other characters that we can also represent with those higher ASCII values from 128 up to 255. And that covers really everything that we would need to represent here in terms of characters through ASCII values. So everything, again, really just comes down to this table here. So in that sense, right, characters are numbers, right? Everything in the end is binary numbers, right? Binary data. So again, that's a very important thing to keep in mind when you're working with strings, which are an array of characters where each character has a numeric ASCII representation. So that's just yet another way of thinking about strings and how we deal with them at the low level, right? In this case, the assembly level. So now with that in mind, let's do the string again. And then let's add in some of those extra things. Now, again, for the string itself, I mean, you're not going to normally go in and use the ASCII values for each character, right? Because that's, more cumbersome, certainly, compared to just writing the string out. But again, when you're dealing with those other things that come up, like a line return or a null terminator, that's when you are going to want to think in terms of the actual ASCII value. So in that sense, I mean, we can write out a string like COMSC 260 without necessarily knowing the mapping, right, for each of these characters. Like, what's the ASCII code for a capital C or a capital O, right? We can do it without knowing that. But again, it is good to know that regardless, and especially for things like line returns and null terminators, right? It is important to know what those ASCII codes are. So if we want to do a little bit more here, and now instead of just having the string itself, on top of that, now we're going to have line return and a null terminator, well, we can just do that here as a comma separated list, right? So O, DH, OAH, that by itself is going to do one line return. And then if we want to have a null terminator, then that's just going to be the number 0 at the end there. So putting it all together, now str3 is the string COMSC 260, but we also have these additional 3 bytes as well on top of the string itself, right? Because in addition to the string itself, we're saying that we want to have one line return, and then we also want to have the null terminator. So now if we look at str3, compared to some of these other things, other strings that we set up, now it's going to be a little bit lengthier because we have some additional things beyond the string COMSC 260 itself. But again, these are things that are very common that we also have. And again, here we have, just a single line return. But if you wanted to have multiple line returns, then you just repeat that pairing of ODH and OAH, where ODH is the carriage return, OAH is the line feed. So again, this is kind of a Windows thing, right? Because other systems, right, do this a little bit differently. But in Windows, we do use both of those two together, right? So the carriage return and first, and then the line feed second, the two together being a line return for us. And again, you can repeat that sequence depending on how many line returns you want to have. So here, right, in this case, we have the same string, we'll call this one str4, same string of COMSC 260, but now we have the pairing of ODH, OAH 3 times. So that's one line return, that's a second line return, that's a third line return, and then the very end is the null terminator, right, 0 itself. Okay, so again, just giving an idea of different things that are possible here. And then let's look, for example, at str4. Now str4, that was the one that had the multiple line returns. So if we go to that location in memory with str4 ampersand or ampersand str4, then we see that. And again, notice here, one nice thing about the memory pane is it's showing actually both things, right? The or at least when you're dealing with a character, meaning an actual readable character like letter C, it's showing you both the character along with the ASCII code for that character in hexadecimal. So, you know, the first character in the string is C, and you're seeing both things, right? So the letter C and the fact that, because again, we usually think in memory in terms of hexadecimal bytes, right? So, and we saw from the table that capital A started at a 65 decimal or 41 hex, which means it would follow that C is at, in this case, 67 decimal or 43 hex. So you see both things, right? The letter and the hexadecimal ASCII value. So we can see the string itself, right? COMSC 260 followed by, you know, the line return sequence, the ODH and OAH, which we had 3 times. So we have OD hex, OA hex, OD hex, OA hex, OD hex, 0A hex. And then after that, we have that 1 0 byte for the null terminator, right? And then from there, we have the rest of, you know, the data segment. But that's the idea. Or if we want to purposely add, you know, an extra value here, so that way we have something. We don't just have a bunch of zeros after the string. Then we can, you know, look at it doing that as well. But again, so in this case, again, we have the string, we have the ODH, OAH 3 times. And then we have the 0 for null terminator, and then we purposely put in that D word 1 just so we don't have a bunch of zeros coming after the end of the string. But that's the idea in terms of how it's stored in memory. And again, you know, we aren't talking about input or output for now, but that just gives you an idea of how you can think about setting those things up, and why it's good to be familiar, at least anyways, with the idea of ASCII codes and a few of the important ones like carriage return, line feed, and then 0, right, here for your null terminator. So again, the 0 is not within quotes because we're talking about the null terminator as opposed to the character 0, which is different. So that gives us an idea of how to start, you know, putting all these things together here. And so we've looked at arrays, we've looked at the different sizes, we've looked at strings now as well, and ASCII codes. And one other very common thing that comes up with arrays, especially as you get into things like loops, is the issue of, well, how many elements are in my array, right? And how do I know that, or how do I determine that information? And you know, there's in general a couple of ways that you can do that here in the assembly environment. We'll see another way later on throughout chapter 4. But one way is using what's called the current location counter, which is the $ symbol in the assembly environment. And the idea is that, and again, we call it the current location counter. What it's storing and what it represents is the first unused address in memory at the time that you're using it. So again, we call it the current location counter, and it's the $ symbol. And what it represents is the first unused location in memory at the point in time that you're using it within the dot data segment. So the value of the $ symbol would change throughout the data segment depending upon where you use it. But the idea is that we can use it to help calculate the number of elements in the array. And to test this, we'll actually move this array up to the top here, and we'll use this array str3 for this example. So this will be a little bit easier to have this at the top of the data segment. And we're actually going to use a couple of things here. So we're going to use that current location counter, which is again just the $ symbol. And we're going to use it along with the what's called a symbolic constant. So this is a constant type value, so it's not a variable. There won't be a size specifier associated with it, although you can, for example, change the value of the constant throughout your your data segment or your code instructions. And so what we can do here is we can have a this constant store or refer to the size of the array, and then we can refer to that, for example, in our code instructions. And so the syntax here is it's kind of like an assignment type statement in C++, is it's the name of the constant on the left, an equal sign, and then the value that we want to assign to it on the right-hand side. So what we're going to do here is we're going to establish this constant, and what we want it to store is the number of elements in the array str3, where the number of elements in the array includes things like the ODH, OAH, and the line and the null terminator. So part of it is going to be this constant here. That's where we're going to ultimately store the result, right? We want this in the end to store the number of characters in str3. And to help us do that, we're going to use that current location counter, which is the $ symbol. So because the idea is that wherever you're using this $ symbol or current location counter, the idea is it's referring to the first unused address in memory at that point in time. So if you have a bunch of things in your data segment, right, and for example, you refer to it after the first variable or the first array, and then later you refer to again after declaring several other arrays, well, in between those 2 points in time, the value or the address of the $ symbol resolves to is going to be different. So it's something that actually changes depending upon where you use it and where you refer to it within your data segment. And so the idea is that because it refers to the first unused address in memory, if we refer to it right after the array has been declared, then that means it's going to be that address that comes right after where the array ends. And if that's the case, and we know that the name of the array refers to the starting address of the array, then we can use those two things together to get the number of elements in the array, right? Because it's similar to something that comes up in C++, right? Because in C++, if you have a pointer to the beginning of the array, and then you have another pointer to the end of the array, right? Then you can do subtraction between those two pointers to get the total number of elements in the array. And we're doing, in effect, a similar type thing here. So in this case, if we want to store, the number of elements from the array str3 in this constant that's called str3 size, then we would just do $symbol minus the name of the array. So the idea is this is going to give us the total number of elements, which includes the string COMSC 260, along with the ODH, OAH, and 0 null terminator, which are taking up an extra 3 bytes, right? But we're including that here in our calculation of the total number of elements. So putting it all together here, if we build this and look at the memory pane, we're going to also see why this works. So we, again, to make this a little bit simpler, we just put this at the top of our data segment here, because where you use the $symbol is important, right, for this to work correctly, since it's a dynamic thing that changes throughout the data segment. So if we go ahead and step into this and go to str3 in memory, so and this str3 was the one that has just a single line return and an alternator. The idea is that we have the string COMSC 260, which is 8 bytes. Then we have the 9th byte for OD, 10th byte for OA, and then the 11th byte for 00, the null terminator. So what it means is that on that line where we said str3 equals $symbol minus str3, at that point in time, the $symbol is going to resolve to address B or address 11. Because at that point in time, right, that would be the first unused location in memory. Because remember, we declared this constant and used this $symbol right below the declaration of str3, which was the first thing that we declared in memory. And at that point in time, we haven't declared any other variables in the data segment. So we can also see the fact that the constant str3 size itself does not take up any memory, right? Because it's a constant rather than a variable that has a size specifier and all that. So it refers to the value, but it's not a variable in the way that str3 is, which is why its value, meaning the value that's in str3 size itself, does not show up here in the memory pane because it's not a variable and not part of memory here. So we have the COMSC 260, and then the OD, OA, and the null terminator. And all of that is part of STR3. So it follows that at that point in time, the first area in memory, or the first address in memory that we're not using, is this address B, or 11. So that's what the $ symbol is going to resolve to. So we're really just doing that address, right, minus the starting address of the array, which is the address here that ends in 0. So the address that ends in B is the address that the $ symbol refers to, and then the address that ends in 0 is what STR3 refers to. And so in effect, right, we're, if you think of it as address 11 minus address 0, well, the result of that is going to give you the number 11, which is the number of elements in STR3 when you include the line return and the null terminator and all that. So it's working correctly here. Or actually, let's do it this way. Because again, that's really, again, that address again, so address 11, right, or address that ends in 11 minus address that ends in 0, and then the other hex symbols are all the same there, except, this one has a B at the end and this one has a 0 at the end. So the end result of that is you're going to get the number 11, which is what's going to be what this constant is going to be referring to, right, or representing as the value 11. And now, so with that in mind, because you're just doing subtraction between these two addresses, now if we say take the value in the constant STR3 size and move that into a register, then we're going to see that we're going to have the correct value of 11, in this case, end up in that register. And it's 11 again because you have the 8 characters in the string plus the 3 bytes here, extra bytes as well. So that's what it's actually doing. And we can refer to those, again, we can refer to the constant, in this case, str3 size, directly in our code instructions. And again, since it's a constant, right, not a variable, and it's not associated with a size specifier, we could in general, potentially use the same constant and move it into registers of different sizes, assuming that, the value that the constant represents is something that register can store, right? So for example, here it stores the number 11, so you could move that into things like EAX or AX or AL, really. But now if we go to the code instructions here, and then we do move EX with that constant str3 size, then we get, again, the value B there is going to end up as the final value in EAX. Or same idea, right? If we used AL, for example. So here we move 0 into EAX, and then we did move that into AL. Same idea, right? You're going to just have the 0 be there, or in AL in terms of the watch window. So that's how the $ symbol works. Okay, and then in next week's class, we'll continue with this, and we'll see also how you can apply this $ symbol or current location counter to other types of arrays, such as word or dword arrays, and then how you could also do it if you have maybe several arrays and you want to store the size of each. So in that case, you could have, a separate constant for each one to store the size of that given array. So we'll look at those kind of things next week.